So, armed with this, we decided to go after bigger questions. What about other source? What about the two modes that we have neglected in the beginning? Right, the higher order modes in the initial conditions. We've only put 50% of the variability. What happens if we increase that to 70%? Do we gain? Okay. And what would happen if we include other sources of uncertainty? Okay, so this was our next UQ experiment. And our original goal was to go after an adaptive sampling. So we focused on these areas, the loop current regions, the sea surface height in that regions, because this is what's telling us about the dynamic in the loop current. And the other region was essentially the other quantity of interest we were looking at is the mixed layer depth near the deep water horizon, that's thread regions. And we were going to essentially let these two criteria drive our sampling. Unfortunately, this guy is very sensitive to wind forcing and changes very quickly. And so it was essentially working the adaptive system so hard that without much gain. And essentially, it's the dependence of this quantity of interest on the uncertain parameter was not very smooth, essentially. And so we abandoned the adaptive quadrature techniques and went to a Latin hypercube samples and a regression type approach. And that worked out very well. So let me show you at least a couple of the response surfaces. This is the sea surface height, the average sea surface height in that red box, in the blue box. And what you're looking at is essentially strengthening or weakening the first mode in the initial conditions and the first mode in the wind forcing, right? And so the samples are in blue and our surface is in color. And what you see is essentially the wind isn't doing much to affect the variability in the sea surface height in that box, but the initial conditions are the ones affecting it. Okay, so you can actually draw a response surface, draw a slice through that response surface. If you looked at the mixed layer depth, then the initial conditions aren't really doing much. At day 30, it's really the wind that is controlling how the mixed layer depth is evolving. Okay. So we had an independent set for validations. And we're doing pretty well in this regression type, where at day 30, 95% of our errors in the sea surface height are less than 6% and or less than 4% for the mixed layer depth. So we're able to validate that the series is reliable for these quantities. Okay. And here you see the evolution of this error in time as well. Okay. So it starts very small and then grows. So our series is good for 30 days. That's good. So we're going to do our analysis for those 30 days. And so for the rest of the talk, I'm going to just show you what you can do with this series, the statistical analysis that you can perform, including, for example, producing a PDF of the output. Now that you have the series, you can artificially inflate the number of samples you have. So instead of 800, you can produce 100,000 because a series is cheap to sum and it's reliable. It's a good approximation of the model. Okay, and so this is what you get with the blue line. The red line is our empirical estimate of the PDF from the actual HiCom simulation, including the validation set. So they're pretty close. We're doing a pretty good job for the mixed layer, for the sea surface height and the mixed layer depth as well. Okay, and they don't look very Gaussian, right? They look skewed quite a bit. And this is their time evolution. Okay, all you have to do this is have a lot of storage. So you can do all this offline analysis. Okay, and you see the accuracy of the empirical estimate of the standard deviation with the polynomial chaos estimate of the standard deviation. They remain very close up to day 30. The errors are negligible. Okay. And now that the variance is available, okay, you can essentially do a sensitivity analysis, also known as ANOVA. So the variance on a polynomial chaos series is just this weight sum. The norm of the basis functions times the square of the polynomials. These are all positive definite quantities. That's beautiful. Because now I can essentially come up with first order sensitivity indices, which essentially tells me what is the variance caused by a particular parameter acting on its own relative to the total variance. And what is the, we can compute another index, TI, which essentially has another ratio where the terms that are included in the sum are of any term that has psi I. It's telling you what is the uncertainty caused by that particular variable when it's interacting with other sources of uncertainty. Okay? And so this is what we see for the sea surface height, the average sea surface height in that box, and the mixed layer depth. That essentially the wind, the first four parameters, which are the amplitude of the wind, control all the variance, all the uncertainty in the sea surface height. It's the total and the first order and the total. They're very close to each other, right? And the other variables, the wind, plays really no role in affecting the sea surface height. Okay. For the mixed layer depth, it's quite the opposite. There is very little input from the first mode, and it depends almost entirely on the first mode of the wind, and a little bit on the second mode. Okay. And this behavior remains true throughout the calculations, actually. So you have total control of the wind, of the initial conditions for the sea surface height, and the wind for the mixed layer depth. Okay. Field quantities. So all these surrogates were produced with the basis pursuit denosing, which is a little bit of an expensive algorithm because of the cross-validation. Okay. So if you want to repeat this at every single space point and time point, that will be an enormous, an expensive calculation. Parallelizable, but expensive. So instead of building these modes, now we do these calculations, we resort to, again, principal component analysis, where you sort of decompose the variability into its spatial components, and it is uncertain components. And so you represent this with a polynomial chaos series. Okay. It's a clever way of doing it, because now all you have to represent is the first leading mode of that decomposition, as opposed to every single spatial points. Okay. And so what you're looking at here is the mean in the sea surface height, okay, at day 30, and the contribution of the 10 leading modes here, okay, that essentially contain about 90% of the variance. And if you look at the variability modes, they are mostly located in the loop current system for mode 1, 3, and 4. And for mode 2, it's really located along the shelves. And now you can estimate the standard deviation in every single point, right? And so this is what you get from this decompositions. And again, because we had a large ensemble set, we could compute the empirical standard deviations, and they look pretty close. Okay, so this is an absolutely reliable way of doing things. Okay. And now you can do the sensitivity analysis over the entire Gulf of Mexico and see which variables, whether it's wind or initial conditions, that are controlling the uncertainty. And so what you're looking at here is the, I think, the first order index for the sea surface height and the mixed layer depth. And it's clear that essentially the wind is controlling the uncertainty in the central Gulf of Mexico. Sorry, it's the initial conditions that are controlling the uncertainty in the central Gulf of Mexico. And it's the wind that is controlling it on the shelves. Okay? And there is very little interaction between the two. For the mixed layer depth, it's the wind that controls it. It has very little influence on the central part of the Gulf of Mexico. And the interaction between them is also very small.